Welcome back to the deep dive. Today, we are doing something a little different.
Yeah.
Usually, we tackle these big abstract concepts, but today we are getting into the trenches. We're looking at a subject that I think genuinely haunts the dreams of every class on and 10 student.
Oh, for sure.
We're talking about science, but specifically that absolute beast of a subject, chemistry.
It definitely has a reputation, doesn't it? You've got the periodic table just staring you down. You've got invisible atoms bouncing around and formulas that look like algebra had a bad day. It's a lot.
It is so overwhelming. And looking at the stack of sources we have today, we've gone through lecture transcripts, study guides, a bunch of student forums. There is one common theme.
Panic.
Panic. Pure, unadulterated panic about the sheer volume of stuff to memorize. But, and this is why we're here, we also found the solution in that research.
We did. And the solution isn't, read the textbook 5 more times. It's about working smarter, not harder.
Right. We're focusing entirely on mnemonics.
Which is pronounced mnemonics. The M is silent.
Thank you. I always want to pronounce the M. Basically, these are cheat codes for your brain.
That's a great way to put it.
We found some incredible shortcuts in the source material rhymes, weird sentences, acronyms, that essentially hack your memory so you can recall these complex chemistry lists instantly.
And just to set the expectations for this deep dive, we aren't just going to rattle off a list and, wish you good luck.
No.
We are going to break down the specific mnemonics for the periodic table, the reactivity series, chemical formulas, and reaction types.
I want the magic tricks.
Yeah.
But I have to be honest with you. I'm skeptical. I've heard these rhymes before, and usually I remember the rhyme, but I forget what the words actually stand for.
That's a very valid concern.
Yeah, like I know Mary had a little lamb, but that doesn't help me pass the science exam.
Right. A mnemonic is useless if you can't decode it. So my job today is to make sure you understand the science behind the magic trick.
Okay.
I want to make sure you don't just say the sentence, but you actually know why sodium is naughty and why argon is a monk.
Okay, I'm listening. Let's jump right into the big one, the periodic table.
Mm-hmm.
If you are in class 9 or 10, there is no escaping this. You have to know the first 20 elements in order by atomic number. You can't just wing it.
No, you absolutely can't. And the order is non-negotiable. The atomic number isn't just a label like a jersey number. It tells you the number of protons, and in a neutral atom, the number of electrons.
So if you swap element 5 and element 6,
We're talking about completely different structures. You're confusing boron with carbon.
which would be a disaster.
Oh,
Okay, so we found a couple of mnemonics in the sources. There's one for elements 1 through 10 that really stood out to me.
The BBC method.
Yeah, from the lecture notes, because it sounds like a news headline.
It's short, punchy, and it's hard to mess up.
All right, hit me with it.
Okay, the sentence is, hi, hello, listen BBC News on Friday night.
Hi, hello, listen BBC News on Friday night. Okay, that flows, but let's slow it down and decode it because this is where I usually get lost.
Good.
Hi and hello.
Hi is hydrogen. Hello is helium. That gets you number 1 and 2.
Easy enough. Listen.
Listen starts with lay. That's lithium. Element number 3.
Then we have BBC. This is 3 elements back to back.
Exactly. BBC. Beryllium, boron, carbon.
Okay, beryllium, boron, carbon. Got it. Then news.
News starts with N nitrogen.
On
O for oxygen.
Friday.
F for fluorine.
And at night?
Ne for neon.
Okay, let me try to run that back. Hi. Hello, listen, BBC News on Friday night. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon.
You nailed it. That is the first 10 elements sorted.
That actually feels manageable. There was another one in the sources, something about a guy named Henry.
Yeah, Happy Henry likes beans brownies baked carefully near our friend's nest. It works if you prefer a story, but I find BBC News is just faster to say when you're panicked in an exam hall.
Agreed. BBC News wins. But we're only halfway there. The syllabus says we need to go up to element 20, calcium.
And this next one is my absolute favorite. It's from a video transcript we analyzed, and it's just weird enough to stick.
No.
To remember elements 11 through 20, you just need to imagine a very badly behaved primate in a kitchen.
I'm intrigued. What's the sentence?
Naughty monkey always sings, please stop clowning around kitchen cabinet.
Naughty monkey always sings, please stop clowning around kitchen cabinet. Okay, that is a mouthful. We need to break this one down slowly.
Let's do it. So element 11, naughty.
Naughty starts with Na, so that must be sodium. Wait, sodium is non.
Yes, and this is why it's a great mnemonic. The symbol comes from the Latin natrium. So naughty is perfect for na.
Okay, that's a good save. So naughty is sodium,
Monkey.
Mdg, magnesium,
Always.
Al, aluminium,
Sings.
Si,
E silicon.
P, phosphorus,
Stop.
S, sulfur,
Clowning.
Co, chlorine,
Around.
Ar, argon.
And then the big finish. Kitchen cabinet.
This is the clever bit. Kitchen starts with K.
What is K in chemistry?
Potassium, another Latin one. Kalium.
Exactly. And cabinet is calcium.
Calcium. So naughty monkey always sings, please stop clowning around kitchen cabinet. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium.
Precision. You have just memorized the electronic configuration sequence for the entire syllabus.
That feels good.
Yeah.
But here is where the skepticism kicks in again. I can recite the list. I can tell you that magnesium is the monkey at number 12. But what do I do with that information?
Right.
Why does it matter that magnesium is number 12 and not 13?
That is the million-dollar question. Memorizing the list is step 1. Step 2 is using that number to understand the atom's personality.
Personality. Atoms have personalities.
They absolutely do. In the source material, there was this brilliant analogy comparing elements to people. Specifically, the lecturer talked about the noble gases, helium, neon, argon. Do you remember what he called them?
He used a very specific Indian term. He called them brahmachari elements.
Oh, right. Brahmachari.
Which, for our global listeners, basically means a celibate monk.
Yeah.
Someone who is totally committed to the solo life.
Exactly. The lecturer said, always single, never ready to mingle.
That is hilarious, but
Yeah.
why? Why are they such loners?
It's physics. It's all about stability. Every atom wants a full outer shell of electrons. For most atoms, that magic number is 8, an octet.
Okay.
Neon, element 10, has 2 electrons inside and 8 outside. It is full, it is perfect, it doesn't need to beg, borrow, or steal electrons, it is content.
So it's a brahmachari because it's self-sufficient.
Precisely. Now look at everyone else. Look at the naughty monkey, sodium, element 11.
Right.
The configuration is 2, 8, and then 1 lonely electron in the outer shell.
That one electron must be so annoying. It's ruining the perfect 8.
It is. It makes sodium unstable. It makes it desperate. It wants to get rid of that 1 electron so badly that it will react with almost anything just to dump it. That's why it's naughty. It's reactive.
Okay, so if the noble gases are the monks, the rest of the periodic table is basically a chaotic dating show.
That is a surprisingly accurate description of chemistry. And that hookup potential is what we call valency. It's the combining capacity of an atom.
Now, I remember staring at valency charts and trying to memorize them, and it was a nightmare. But you're saying there's a trick to calculate this on the fly.
There is. And you don't need a chart. You just need your fingers and that naughty monkey list. You just look at the valence electrons, the ones in the outermost shell.
Okay, walk me through the rule. I'm in an exam. I need the valency of aluminium.
Okay, aluminium. Naughty monkey always. It's number 13.
Okay.
Configuration is 2, 8, 3. How many valence electrons?
3.
The rule is simple. If the number is 1, 2, 3, or 4, the valency is that number.
So aluminium's valency is just 3.
Yes, because it's easier for it to lose 3 electrons than to try and find 5 new ones.
Okay, what if it's on the other side? Like chlorine,
Yeah.
clowning, element 17. So
yeah.
2, 8, 7.
If the number is more than 4, so 5, 6, or 7, you do a tiny bit of math. You subtract that number from 8. Because 8 is the dream. 8 is the stable octet. Chlorine has 7. How many more does it need to reach 8?
Just 1.
Exactly. 8 minus 7 is 1. The valency of chlorine is 1.
That is so much easier. So 1 to 4, the number is the score. More than 4, subtract from 8.
Correct. But there's one tricky exception, thanks to our brahmachari friends.
Wow.
Helium.
Right, helium. It's element number 2. So it has 2 valence electrons. By my rule, its valency should be 2.
Logical, but wrong. Remember, helium only has 1 shell, the K shell, and that shell is tiny. It can only hold 2 electrons.
Ah, so if it has 2, it's already full.
It's already full. It's a brahmachari. It doesn't want to combine.
So its combining capacity, its valency is 0.
0. That's the only one you really need to watch out for.
Got it. Okay, so we know the actors, the elements, and their motivation valency. Now let's talk about the drama, the reactions.
The chemical reactions. This is where class 10 really kicks it up a notch.
And one of the biggest headaches is figuring out if a reaction will actually happen. You know, those displacement reactions where one metal kicks another one out. It just feels random.
It's not random. Think of it like a wrestling match.
Okay.
A stronger wrestler can push a weaker wrestler out of the ring, but a weak wrestler can't move a strong one. To know who's strong, You need the reactivity series.
And we have a mnemonic for that. The zoo theme.
Yes.
Please send cats, monkeys, and zebras in large cages.
I love this one. Let's decode the zoo from most reactive down to least reactive.
Please is potassium, the boss.
Send is sodium.
Cats is calcium.
Monkeys is magnesium.
And zebras is zinc.
In is iron.
Large is lead.
And cages is copper.
Please send cats, monkeys, and zebras in large cages.
Okay, let's apply this, because this is where I'd lose marks. Say the exam question asks, what happens when you put an iron nail into a copper sulfate solution?
Okay, check your cheat code. Iron is in. Copper is cages. Who comes first? Please send cats, monkeys, and zebras in large cages. Iron comes before copper.
So iron is higher up. It is more reactive. It's stronger.
So it kicks the copper out?
It kicks the copper out. The iron dissolves. The solution changes color. You get iron sulfate.
Okay, now flip it. What if I put a copper wire into iron sulfate solution?
Well, copper is cages. It's way down at the bottom. It's the weaker wrestler.
So nothing happens.
Nothing happens. It's not strong enough to kick iron out.
So the answer is no reaction.
Exactly. And you figured that out just by remembering zebras in large cages.
That is powerful. It really is.
I think that
Okay, while we're on reactions, the sources also gave us a great acronym for remembering the different types of reactions.
Yes, the acronym is SCORARD. SCORD.
Which stands for?
S is for synthesis, or your textbook might call it combination.
C is for combustion, burning stuff.
O is for oxidation, R is for reduction.
And D is for decomposition, breaking stuff down.
That covers the main bases. And it's worth pausing on the O and R, oxidation and reduction. They almost always happen together.
They called it redox, right?
Yes. Reduction and oxidation. Redox. The simplest way to remember it at this level is just to follow the oxygen.
Follow the oxygen.
Think of oxygen as a clingy friend. If you gain the clingy friend, you are oxidized.
Gaining oxygen, oxidation. Makes sense.
If you lose the clingy friend, you are reduced. You've reduced your baggage.
I like that. Lose the baggage, you're reduced.
Yeah.
Gain the baggage, you're oxidized.
Yeah.
Simple.
Spot on.
Okay, moving on. We've done elements, valency, reactivity. Now we have to actually write the chemical formulas. This is where I feel like a lot of students lose silly marks.
Oh, it's the classic tragedy.
Yeah, you know the chemistry, but you write sodium sulfate as NaSO44 instead of NaSOASO44, and the whole thing is wrong.
But you can avoid this 100% of the time if you just trust the criss-cross method.
Okay, walk us through it visually. Let's do aluminium oxide.
Perfect. Step 1, write the symbols side by side. Al and O.
Done. Al and O.
Step 2, write their valencies below them. We just did these.
Aluminium. Always. Element 13. Valency 3. Oxygen. On
All right,
element 8 needs 2, so valency 2.
Perfect. So write a big 3 under Al and a big 2 under O.
Al has a 3. O has a 2.
Step 3, crisscross. You basically swap them, give aluminiums 3 to the oxygen, give oxygens 2 to the aluminium.
So Al takes the 2, O takes the 3. The result is Al2O333.
Correct. Al2O333.
But there's a catch, isn't there? The sources mention something about respecting certain groups. This is where I see people messing up with brackets.
Yes, the polyatomic ions. These are like little gangs of atoms that act as one unit. Sulfate, silophorin-3, nitrate, hydroxide, $.
The tip in the lecture notes was, give them respect, which means...
Put them in brackets. If you need more than one of them, you must use brackets. Let's look at calcium nitrate.
Okay. Calcium is calci, valency 2. Nitrate is NO333, valency 1.
Crisscross them. The calcium gets the 1, the nitrate gets the 2.
Okay, so if I just write it out, TeLa-TaNO32, that looks like calcium nitrogen with 32 oxygens.
Exactly. It's a meth, so you have to put brackets around the whole nitrate gang, NO3O2.
Oh,
put a little
you are respecting the group. I like that.
Respect the gang. If
Yeah.
you're inviting the gang to your party twice, put a fence around them.
Got it. Okay, we are cruising, but now we have to face the final boss.
The mole.
The topic that makes grown adults shudder. The mole concept. Even saying it sounds complicated.
It feels that way, but the sources break it down with a really simple analogy that demystifies it. They compare the mole to a dozen.
A dozen. Okay, let's play this out. If I say I have a dozen bananas, how many do I have?
12.
A dozen Ferraris.
Just 12?
A dozen atoms.
Also 12.
Okay, so dozen is just a word that stands for the number 12.
Exactly. And mole is the exact same thing. It is just a word that stands for a number. It just happens to be a really, really, really big number.
Avogadro's number.
6.022 times 1022.
That is a terrifying number. Why do chemists need a number that big? Why can't we just count atoms in dozens?
Because atoms are too small. You can't put a dozen atoms on a scale and see the needle move. But, and this is the magic of the mole, that specific number wasn't chosen randomly. It's a bridge.
A bridge between what?
Between the invisible world of atoms and the real world of grams. Look at carbon. Its atomic mass is 12U.
Right.
That's for one atom. Useless in a lab. But if you gather 1 mole of carbon atoms, do you know how much they weigh?
Don't tell me. 12 grams.
Exactly 12 grams.
Wait, that's the same number.
That's the trick. The number stays the same. The unit just changes from U to grams.
So let me test this. Water. H2O's. Hydrogen is 1. Oxygen is 16. So 1 molecule is $1 plus 1 plus 16 equals 18U.
Correct. So if I have 1 mole of water molecules in a glass, how much does it weigh?
18 grams.
18 grams. You just calculated molar mass.
That is actually a huge aha moment. It's just the atomic mass with a G slapped on the end.
That is literally it. It makes the problems manageable. If a question says 5 moles of water, you just take the weight of 1 mole, 18 grams, and multiply by 5.
$18 times $5, 90 grams.
Boom!
Yeah.
You just solved a mole concept problem without breaking a sweat.
Okay, my brain is officially full, but in a good way.
Right.
Let's do a lightning round recap of the cheat codes. I want to see if I can do this without looking at my notes.
Let's do it. I'll prompt you. Elements 1 to 10, the news channel.
All right. Hello, listen BBC News on Friday night.
Elements 11 to 20, the Praymate.
Naughty Monkey always sings, please stop clowning around kitchen cabinet.
Reactivity, the zoo fight.
Please send cats, monkeys, and zebras in large cages.
Reaction types, the acronym.
SCORDIA. Synthesis, combustion, oxidation, reduction, decomposition.
And finally, the method for formulas.
Criss-cross. And respect the gang.
You passed.
I feel like I passed. You know, chemistry feels a lot less intimidating when you have these stories to hang the facts on.
It really does. But I want to leave the listener with one thought. These mnemonics are the entry point. They help you survive the exam. But real chemistry is asking why.
That is such an important point. Why is sodium naughty?
Because of that electron structure. Why does iron kick out copper? Because of its reactivity. The mnemonics tell you what happens, but the concepts tell you why.
Use the cheat code to get the answer, but understand the logic to become a pro.
And here's a provocative question for you to chew on. We talked about atoms that steal electrons, like sodium, and atoms that are brahmachari monks.
Right.
Think about carbon. Element 6, configuration 2, 4. It has 4 valence electrons.
It's right in the middle. That's an awkward spot.
It is. Does it steal 4 electrons? That's super hard. Does it give away 4? That requires massive energy.
So what does it do?
It chooses a third path. It shares. But how that sharing becomes the basis for basically all life on Earth, that is the mystery of carbon and its compounds.
That is a tease for a whole other deep dive. Well, thank you for guiding us through the maze of Class 9 and 10 chemistry.
My pleasure.
To our listener, go mix some chemicals, metaphorically, of course, and use these cheat codes.
Keep learning.
Thanks for diving deep with us. We'll catch you next time.